If I want to find the total potential energy, I add up those two charges, calculate K, Q1, Q2 over R. I do these charges, K, Q2, Q3 over R, and then these two charges, K, Q1, Q3 over R, and then I add up those three. We had a homework problem somewhere that somebody worked through some problems. You okay with this sort of thing? Yeah. Finding the total potential energy. We did do electric potential due to a rod where you had to take the integral of a rod. You remember this, where we had a rod and we said what is the potential at this point, and then we did the integral of KQ over R. We won't see that at all in the exam, and don't worry about doing a derivation prior to the exam either. Yeah. Is that, or would you rather? No. Okay. All right. And then equal potential lines. Equal potential lines, remember, if I have a charge Q, we draw the field lines. If it's a positive charge, our field lines look like this. But also in this chapter, we saw equal potential lines. These are points where the potential is all the same. So along these field lines, the potential is all the same. You might have to interpret an equal potential line or interpret field lines. Notice that here the potential is smaller or is bigger as you get closer to the charge as well. Alright, so if I have different points, we saw some questions like this. If I have points here, here, and here, A, B, and C, the one with the bigger potential is point A because it's closer to the charge. And then also we had electric fields. We can find the electric field due to a potential function. So let's say I have a potential function is 3x plus 4xy squared. If I want to know the electric field in a particular direction is the negative of the partial derivative of the potential function with respect to that particular direction. So for example here, Ex would be negative the derivative of this function with respect to x. That's going to be, what's it going to be? 3 plus 4y squared, right? And then Ey is going to be the negative of what? 8xy, right. So you just take the derivative of that function with respect to that particular variable. These are called partial derivatives, but they're a lot like derivatives. You just imagine that the other variables are constants. So here I said the derivative of 3x with respect to x is 3, right? That's 3, you remember, no, derivatives, right? Polynomials. Right? Here, I just imagine that the y squared is constant. So 4y squared times x, the derivative of that is just 4y squared. Right, so you just hold whatever variable is not in your partial to be constant. And so here, my electric field then in vector notation would be, let's say that I take x equal 2, y equals 0. All right, I just plug these variables in. So this would be negative 3i. That's plugging in those numbers for Ex. That's it. And minus 0, plus 0j. Because when I plug in those numbers here, I have 8 times 2 times 0, which gives me 0. Okay, you'll have all these questions. I said there's actually not that many topics in this, so all of this stuff will be on the exam. So make sure that you can do all this. We'll also have capacitance. A couple things about capacitance. We define capacitance as Q is equal to CV, and then also C is equal to kappa epsilon naught A over D. You should look over those concept tests. They're not online now, but I'm going to put them online when I get back to my office this morning. So look over the concept tests regarding capacitance and those series of questions that we had about having different capacitors in series or in parallel and what happens to the charge on them or the voltage on them. We can look at some problems like that this morning if you want. So you'll need to know how to calculate the capacitance given the dimensions, and then also given this law, this rule, what is the capacitance. You'll have circuits as well. You could see some simple circuits like capacitors in series find the charge or voltage on them are also capacitors in parallel. Alright, you'll need to know those rules for capacitors in series. The equivalent is equal to 1 over C1 plus 1 over C2 plus however many capacitors you have. The capacitors in series have the same charge. Capacitors in series, for capacitors in series, Q equals CV, and then also V total is equal to V1 plus V2. That means, like, for example, if I have 12 volts here, I have to have 8 volts. If I have 12 volts and 8 volts here, that means I have to have 4 volts here. Alright, for capacitors in parallel, the equivalent is just the sum of the individual capacitors. Capacitors in parallel have the same voltage. For capacitors in parallel, Q equals CV, and then Q equivalent, that's the charge on the equivalent capacitor, is equal to Q1 plus Q2. So I don't really use that very much, but just to make this better. Okay, so you can see capacitors in series or parallel. We'll look at a more complicated circuit later, which will probably be what you have the most trouble with, are those combination circuits. Alright, we've worked through a couple different problems with those combination circuits, and you'll certainly have one on Monday. You'll also have a simpler circuit as well, where it's either series or parallel. Alright, can I go on? Yeah. So you'll have a circuit, one of these, we've seen them in various tests and what have you, but a circuit where you have capacitors laid out maybe in a funky way like this. Something like that. You'll probably have more capacitors than that. We'll go back in just a bit after we finish going through all the different topics, and we'll work through some examples like this. But a capacitor circuit may be laid out something like this, where you have to find the charge and the voltage on all the capacitors. You'll also need to find the energy maybe on one of the capacitors. Remember that to find the energy on a capacitor, we went over this very briefly, it's just 1/2 CV squared. And that's on your equation sheet, of course, but you'll just, if you find the capacitance and then the voltage of a particular capacitor, you just find the energy in that way. Alright, let's go ahead and do this one actually. Let me put in some numbers here. Let's put another capacitor. The first thing would be just to redraw this. What is it? You want to add another?
I was like, man, this is so easy. Then you do the unknowns.
Yeah, no, let me think of some numbers that'll work really well for us. Alright, so let's do this circuit, and I want to know what is the charge and what is the voltage on each of these capacitors. The first step in this will just be to redraw it. And often students will get messed up in this. So you want to start with your battery, and then you go along and you draw everything until you get to a break in the or a junction in the circuit. So right here I have a junction, and I have 2 branches that go from this junction. So I'm going to go up here. I'm going to draw those 2 branches right here. Alright, you want to practice this. So I would go through the old tests, and on every test, every semester since the beginning of time, I always give them a problem like this. So there's lots of examples for you to go through. I would start looking at it without looking at the solution first, and just try to redraw it first, and try to work through it, and then go back and look and see if you got the answers right. Because you always learn better by making mistakes. Alright, so here, I'm going to take the top branch first. I'm going to have a 3, and then another 3, following along here, until I reach the first junction. So then I reach another junction. So I draw my 3, I draw my 3, and then I reach another junction right here. So this is that junction. And then I can draw those. I have a 1 and a 2. So I have a 3 microfarad, a 3 microfarad, a 1 microfarad, and a 2 microfarad. And down here, this was a 6 microfarad. And then everything sort of seems to come back together from there. Because once I go through this 1 and the 2, then I have a clear path back to the battery. There's nothing else between this 2 microfarad capacitor and the battery, or the 1 microfarad capacitor and the battery. So all those junctions sort of come back together. All right, and then what's on the bottom branch of this circuit? Only the 2 microfarad capacitor. Right. Now let's say this is 12 volts. All right, now I would want to find the equivalent. I'm going to start with which part of this circuit to find the equivalent? Right, I'm going to start with the 1 and the 2 in parallel. 1 plus 2 equals 3. All right, so 1 plus 2 here is equal to 3. And I have a 3, a 3, and a 3. That whole thing is 1. 1 over 3 equals 1 over 3 plus 1 over 3. I've given y'all the fractions that I like to use. I would take a look at those. I can rewrite them in this note if you want. So then I have a 1 and a 2, which is going to give me 3 microfarads, and then a 3 and a 6, which is 2 microfarads. Let me write all that out. So I find it really useful to redraw my circuit each time. You might not want to draw all the steps just because it takes a lot of time, but as you're practicing, it's probably a good idea. All right, so this is 6, 3, 3, and 3 microfarads, 2 microfarads, 12 volts, six microfarads, and then I'm left with a 6 and a 3. And then I'm left with a 2 in the very end. So my equivalent capacitance here is 2 microfarads. On 12 volts. All right. On this 2 microfarad capacitor, I'm going to have 24 microcoulombs. All right, once you get all these circuits drawn, you start stepping backwards. Capacitors in series have the same charge, so I'm going to have 24 microcoulombs here and 24 microcoulombs here. All right, that means that I'm going to have 4 volts and 8 volts. Since I have 12 volts across the battery, they should add up. You can also look at how they're distributed, the capacitances. So this has half the capacitance, so it has twice the voltage. You know, 8 and 4 have to add up equal to 12. 8 is twice 4. So you might not need to find the charges. Or you can just think about how the voltages are distributed. Here, this 3 microfarad is made up of these two. So these both have 8 volts and 8 volts. And this has 4 volts. So this is the same, 8 volts, 4 volts. These three microfarad capacitors, they all share this 8 volts, so each of them is going to have what? Not 2. What's a third of 8? 8 what? 8 over 3, right. So they're each going to have 8/3 of a volt. All right, so they have 8 divided by 3 volts, 8/3 volts, 8/3 volts. Just simply because the voltage is split 3 ways, because there are 3 capacitors, not because the capacitors are 3 microfarads. All right, and then these each have 8/3 volts as well, because they're in parallel. So once you get all the voltages, which now we have, to find the charges, you just say Q equals CV. That's it. That's all that question. But the hard part for a lot of students is this first step. Is just getting from that circuit drawn out on a grid to a circuit that looks more like what we've been doing in class. But often if you're doing electrical circuits, they'll look like this. And so often they're even more complicated because they'll have things sort of drawn across an angle like that. Alright? I do get partial credit, so you know, it should be pretty easy for you to get at least half the partial credit, because if you get the voltages right, then, or if you get the voltages, then the Q's are just C times the voltages. So I'll give you some amount of partial credit if you just calculate those charges correctly. If I can do this, you will have one. I would practice all those old tests, and we'll have some time at the end. If you want to go back and we can practice them, we can. All right, the next step that we'll have are resistances and current. Remember, current is Q over T. That's how we define current. And then also by Ohm's law, our potential is V equals IR. And then you also need to know that the resistance is rho L over A. So we have these three basic definitions for current. We define actually resistance by Ohm's law. R is equal to V over I. That was actually how Ohm's law is actually stated. R is defined as V over I. But we usually write it like this. And then our resistance is also defined by the dimensions on the resistor. R is equal to rho L over A. You have some conceptual questions sort of asking about the resistance of an object. If you change its dimensions, what happens to the resistance? You'll just need to know that. So if you increase the length, you increase the resistance. If you increase cross-sectional area, you decrease the resistance. You have problems like this. They'll be on the concept test. I'll look over this. Yeah, that's it. I think that's all chapter 3. It was a pretty short chapter, but just on current and resistance. Okay? You okay with this? You have some basic resistors in series or parallel. You'll have two of these, one of each. Say something like this, 12 volts, 2 or 3 resistors. Let's say this is 2 ohms, 4 ohms. What is the current? What is the voltage across each of these? What's the current in these resistors? 2 amps, right? I find the equivalent resistance. Let me write down those rules actually for capacitors in series. Capacitors in series, the equivalent is equal to R1 plus R2. The capacitors in series have the same current. Capacitors in series, V equals IR. And V total is equal to V1 plus V2 plus however many resistors you have in series. So here, for example, our equivalent resistance would be 6 ohms. 2 plus 4 is 6 ohms. That gives us the current here, which is going to be V over R. That's 12 volts over 6 ohms, which is 2 amps. Because these resistors are in series, they all have 2 amps. So I have 2 amps here and 2 amps here. So the voltage here is V is equal to IR. It's 4, right? 2 amps times 2 ohms is 4 volts. And here it's what? It's 8 volts, right? These should be pretty simple. I want everybody to get these, right? It's sort of like a give me question, right? Gonna get these? Okay. All right. The other type that you'll have will be parallel. You have 2 or 3 resistors in parallel. Let's say we have 3 ohms, 6 ohms, 12 volts. Be able to list the voltage and the current in all the resistors as well as the total current. Somebody tell me the total current in this circuit? Right. I find the equivalent resistance, a 3 and a 6 in parallel, that's 2, right? If I have 2 ohms and 12 volts, 12 divided by 2 is 6. So I have a current here of 6 amps. What's my voltage here? 12 and 12. Let's write down those rules. The equivalent is 1 over R1 plus 1 over R2. Resistors in parallel have the same voltage. You might have some multiple choice questions just about how resistors in parallel and series operate. Or excuse me, no. How capacitors in series and parallel operate. I told you we'd have no multiple choice, right? Let me make a note of that. check your test. That's right. Alright. Note to myself. Alright. I have the same voltage, V equals IR, and then I total equals I1 plus I2 plus dot, dot, dot. We'll use this a lot in the next test. Alright, so here, these each have 12 volts, because resistors in parallel have the same voltage. I know the equivalent is equal to 1 over 1 over 3 plus 1 over 6, that's 2 ohms. I also know that our current here is 12 volts over 2 ohms, which is 6 amps. And I can find the current here, 12 over 3 is 4 amps, 12 over 6 is 2 amps. Fortunately, it works out right. 4 plus 2 is equal to 6, as it should be, because resistors in parallel, the currents add up to equal to total current. That was that fourth rule. Okay? There's a lot of sort of steps that you have to go through, but hopefully you can just look at it and say, well, the voltage here is 12 and 12, so I have 4 and 2 amps, and 4 plus 2 add up equals 6. Alright? Let me give you those fractions. I've given them to you before, but for capacitors in series, resistors in parallel, I like to use some common numbers. 1 over 3 plus 1 over 6, that equals 2. 1 over 4 plus 1 over 4, that's equal to 2. 1 over 2 plus 1 over 2, that's equal to 1. It's equal to 1. 1 over what is it, 1 over 3 plus 1 over 6 plus 1 over 2. Isn't that right? That's 4 plus 2 plus 6. Yeah, that's equal to 1. I like to use those. I mean, I'm not restricted to these, of course. I can use whatever. But to make it simpler, I'll use those. Okay? I want nice even numbers for y'all, so it's easy. Alrighty? What do y'all feel like you need help in right now? What do y'all spend more time on? That's everything. Test is about, gosh, I think there were five or six previous months, and like 13 or 14 multiple choice, but I'll count them this year. You get 1 3. Or they might be. You want to look at some of those capacitors? Yeah. All right, so let's say that I have 3 charges. Let's say 1 nanocoulomb charge here, a minus 2 nanocoulomb charge here, and a 3 nanocoulomb charge here. And I want to know, let's do 2 problems. Let's first find the potential at this point. We'll say that this is 3 meters. We'll call this 4 meters. And I want to know the potential at this point. First, what is V? And then we'll address the potential energy, which, it could be the same problem. Like
I wanted to know this one too.
okay. Well, to find the potential at that point, I just do the sum of KQ over R. Alright, so that's going to be 9 times 10 to the 9th. That's K times negative 2 times 10 to the minus 9. Make sure you get the negative number. It's a scalar quantity. We include that negative number. Divided by the distance, which is going to be this distance, which is 3 meters. plus, looking at this charge now, 9 times 10 to the 9th, 3 times 10 to the minus 9, divided by 4 meters. Yeah. Oh, this should be positive 9. K is 10 to the positive. Yeah, that's the Coulomb's constant. It's on your equation sheet. And then this one is 9 times 10 to the 9th, 1 times 10 to the minus 9, divided by the distance, which is 5 meters. Notice I have this 3, 4, 5 triangle right here, so this distance is 5 meters. And then I just add all those up. These are simple. Usually I'll try to give you numbers that'll cancel out a lot, so it's nice if you want to write them out, and then you can see that these cancel. This, I have a 3 left, that gets rid of that, so it's equal to negative 6. That cancels, plus 27 over 4. That cancels, plus 9/5. So whatever that is, 120 plus whatever. All right. That's how you find the potential. So that would be in volts. All right. Now to do the potential energy, you have 3 pairs of charges. You have this pair of charges. You have this pair of charges, and then you also have this pair of charges. And each of them has an inherent potential energy contained just within that configuration, because there are forces at play. They contain a certain amount of potential energy. And you just calculate the potential energy for each pair, and then you add all 3 up. Right? Your potential energy, can I erase all this? So there's a problem like this. It's useful to be able to find this potential energy because within molecules and atoms you have a certain amount of potential energy, and it's due to the configuration of charges, how they're attracted to one another, those charges. I think y'all get more into that in PChem. So potential energy is KQQ over R. And so each of these has a charge and a distance, and so we just add those up. So for example, doing the 1 and the 3, which I circled in red there, that's 9 times 10 to the 9th, 1 times 10 to the minus 9, 3 times 10 to the minus 9, divided by 3 meters, plus the third term. Do I need to write the third term? You get the idea? Where would be
third term would be negative 2 and 3.
Negative 2 times 10 to the minus 9, 3 times 10 to the minus 9, divided by 5, also times that 9 times 10 to the minus 9 times 10 to the positive 9. Okay? You have one like this. That should be another easy. I mean, you know what the questions are on the test. There's a capacitor circuit. There will be capacitors in series or in parallel. Just a simpler circuit, not like a big complicated circuit. You'll have potential and potential energy. You'll have resistors in series and parallel. 2 circuits, 2 simple circuits. That's an easy test, right? Like everything you know. I mean, if you're prepared, if you know how to do these things. All right. You want to look at some of those circuits? We have a few minutes. Y'all want to look through just redrawing the circuits? Can we do that? I think that's probably useful. So I'm just going to pull up an old exam. Or did I have one on this one? Oh yeah, here we go. So I had this one. I want you to consider the circuit and then complete the table. Listen, whenever I draw circuits, I always imagine starting on the positive side. So I start on the positive side, and then I start redrawing from that direction. So I have my 12-volt battery there, and I follow along until I come to the first junction. I'm going to draw that. And that junction has 2 branches. Alright, and then I can redraw that. I have a C3 right here. And then I have, on the other branch, C1 and C2. C3, C1, and C2. And then, coming back here, this is it seems a little misleading because this one capacitor is sort of drawn at an angle. But often in circuits that you see in circuit diagrams, like in schematics, they'll draw them like that just to save space in the schematics. So you need to sort of train yourself to look at them. Now in this case, I can make it a little simpler by just shifting it up like that and just drawing it horizontally. But we're going to make it like that. So once I go through C1 and C2, notice that I can go straight back to the battery. And so from C1 to C2, I should have a clear path back to the battery. Now looking here, I have C3 drawn here, I come to another branch. So that means that after C3, I'm going to have another parallel branch that will open up. So after C3, which is right here, I'm going to have a junction right here. And that will include C4 and C5. And then everything closes up, and it all goes back to the battery. So that circuit is the same as those 2 circuits right there. Yeah, Josh?
Would it look any different if you, instead of rotating C5, like the horizontal, you rotate it vertically?
No, it doesn't matter.
It doesn't matter.
Like you can move things around as long as you don't cross over elements. I could draw this like this, I could draw it like this, I could draw it at an angle as long as this point doesn't cross this capacitor, or this point doesn't cross, this junction right here. You can redraw them in any way. I could also draw, I could draw this capacitor like coming off of there. Y'all follow what I mean? I can move a point in the circuit anywhere on a wire as long as I don't cross over another element. And then that changes substantially what the circuit is doing. Alright, and then from there you find the equivalent capacitance, and then you find the charges on all the individual capacitors. Okay, you want to look at another one? Practice really helps with these. Alright, so here I have my 12-volt battery. Again, I always start on the positive side. It doesn't really matter. You can start on the negative side, but it's a little, I don't know. That's just what I do. Alright, so C5 is there. And then I come along and I come into a junction. This one's sort of laid out a little more readily. And it breaks into 2. Like that. On this left one, I have another junction where I get C1 and C2. Those actually come back together. And then over here I get C4 and C3. And then after this C3, it all goes back to the battery. Likewise, C1 and C2, they get clear paths back to the battery. So I can get that if I close it off like that. Alright, we'll look at another one. Practice really helps with these. Yeah, this one's pretty easy. That was like, I was nice. I was a nice person. Yeah, yours only worth that much, I'm pretty sure. Alright, so here I draw my battery. I start with C1. And then I follow C1 till I get to the first junction. At this junction, I get 2 branches. Right? On the bottom branch, I get C1. Or excuse me, C3. I get C3. right here, and then I get C2 and C4. And then I follow these back until I come to another junction. Alright, now this part is a little bit different. I can imagine, I think we went through one in class like this, I can imagine that this collapses down to a point. I can do that because there's no capacitors here, and so I could bring those 2 points together, and that's actually where that branch ends. And then I start a new branch. That's going to have C5 and C6 and C7 in it. And then I think that's the end. Yeah, that's the end. Alright. Look at another. Yeah. I clear this? Yes. C, is that what you said? Alright, S12, S11. I know this is fast, but the solutions are all online if you want to go back and review some of these, which I'd recommend that you do. Watch, I'll try this one right quick. I'm going to start, I'll just draw up to the first junction. Either on your paper or on your mind. I think we've done one similar to this actually. Yeah. So this is my first junction here. Just here, I break into 2 branches with that parallel branch. Up here, I'm going to have what? C2. And then I'm going to do what after C2? Right, I'm going to break into another branch, C5 and C4. And then those are going to come back together. And then down here I just have C3. And then that's it. Alright. Some people can look at a circuit like this and understand sort of how the voltages are distributed, but I find that most people can't. You really need to sort of draw it out like this. Alright. I clear this? Alright. I think that's probably good for now. Is that okay for now? Yeah. Okay. That's the test for y'all. Okay. 7:15. And listen, I haven't gotten confirmation. I will shout today about whether or not we have it in this room or in the auditorium. And as soon as I get that, I'm going to email you. Okay. I'll certainly email you. Yeah. The auditorium is room 101. It's that big room. The big room? Yeah. Huge auditorium, yeah. Bring a jacket. Sometimes it's kind of chilly in that room. But nice comfy chair, big desk and stuff. I think you'll be fine. Well, we'll still start at 7:15, okay? You have a good day, okay? If you want to bring in more food donations, you can do that up till Monday afternoon about 4.